proportional to the square of its amplitude. Therefore, the relative intensity of two waves is proportional to the square of the ratio of their amplitudes. Another thing is finding the path difference between two waves, and a lot of common questions are asked on this particular concept. To find the path difference of a wave, what we do is we calculate the actual difference in path lengths. The base distance that we use is that traveling in air. However, if oil or water or glass is given, then the differences in those particular mediums may be exaggerated or less as related to the optical factor which is associated with those mediums. So make sure that you take into account whether the two waves are traveling in glass or in air or in water or oil or whatever medium is given to you. Now let's talk about the variation and interference patterns that we see. Young's double slit experiment. First, let's describe this experiment so we understand what we're talking about. Assuming that you have a source of light, a point source which is placed at the axis. From those, wavefronts emerge. We place a screen over here which has two holes equidistant from the source. When the wavefronts hit those particular small apertures, they get transformed into circular waves. These circular waves interfere with each other. At some points they interfere constructively, at other points they interfere destructively. When Young originally carried out this experiment, he placed a screen at a certain distance and found that alternate light and dark bands were present on that particular screen. To explain this, let's understand the figure that we've been given. From those two slits, we assume circular wavefronts to emerge. At some points, those wavefronts are interfering constructively. That is, both have their high points at that particular place. There are other points which are consistently antinodes. That is, the waves are interfering destructively at those points throughout time. At the constructive wavefronts, we see light bands. At the destructive wavefronts, we see dark bands. Therefore, if we place a screen at some particular instant, we'll see alternate dark and light fringes. These of course depend on the wavelength and the slit of the widths. As the wavelengths keep increasing, we see that the distance between consecutive light and dark bands increase. Also, as the slits come closer to each other, the distance between the light and dark bands increase. How do we explain this? Again, interference and path difference. How do we find the path difference at different points of the intersection pattern? Consider a point A. Its distance from the first slit is say 5 lambda. From the other slit S2, we again count the number of wavefronts of distance and we find that the distance is 6 lambda. Since the angle is almost the same for both of them, the path difference is effectively lambda. In this case, the interference would have been constructive, since it is proportional to n lambda, n an integer. If it was proportional to n plus half lambda, then the interference would have been destructive and we would have seen a dark band at that particular point. Moving on to strings and sound waves. Some of the common areas that we have to focus on. The energy of those waves. There are standard formulae which you must know how to apply and understand in these. The energy varies across the string in a standing wave. At some points there is potential energy plus kinetic energy of some magnitude. At other points there may be only potential or only kinetic energy. We should be clear about how to calculate these energies and how they are related to the amplitudes and frequencies at any point. You also have a few cases of the Doppler effect where the concepts are essentially the same as before. Make sure that you completely understand the meaning of the wave equation and are able to apply it in any given situation. All the wave parameters and their meanings should be known, as well as the common definitions. Examine a standing wave. You have two waves in opposite directions which are interfering with each other. Their superposition leads to a standing wave. That standing wave has some nodes where those points remain permanently at rest and are not displaced at all. They also have antinodes, where those points are displaced to a greater amplitude than either of the waves individually. You may also have two-dimensional standing waves. Examine the cases that are shown for n is equal to 1, 2 and 3. when you have a fixed end and a free end, the reflections of a traveling wave from those ends are somewhat different. If a wave is generated from one end and it hits a fixed end, it tends to reverse its original orientation. Whereas when it is a free end, since that particular point is free to move up and down, it does not get reflected in the opposite direction. Consider the transmission and reflection of a traveling wave in media which have different densities. Suppose there are two strings which have a common point. One of the strings is rarer, the other is denser. A wave moving on the rarer string, when it goes to the denser string, will split up into two waves. One will be the transmitted wave, which continues on in the denser string. The other will be the reflected wave in the lighter string. When moving from rarer to denser, the denser wave has a lower amplitude and the same sign, whereas the reflected wave has a lower amplitude and the opposite sign. In the reverse case, when a wave is moving from the denser string to the rarer string, the transmitted wave has a higher amplitude in the rarer string, and the reflected wave has a lower amplitude but is not reversed in terms of sign. Let's demonstrate the Doppler effect. When we have a stationary source, which is a point source emitting waves in all directions, the frequencies on both sides are equal. However, when that source is moving to a particular place, then in the direction to which it is moving, the frequency will increase since there are more waves per unit time. And in the other direction, the frequency will appear to be lesser. Similarly, for an object moving towards the source, since we are encountering more waves per unit time, its frequency increases. And the reverse for the object moving away from the source. It's a similar case when the source is moving away or towards the object. In the formula, the relative motion of the source and the object have different places, and we must be sure of their signs. Now we move on to electricity and magnetism. This is without doubt one of the most important areas of study, comparable only to mechanics. The JEE regularly asks many questions based on electricity and magnetism because of the wide breadth in this particular area and the numerous concepts on which new and innovative problems can be based. So be sure that this is one of your strong points and that you clearly understand all the different concepts that are related to electricity and magnetism. What is an electric field? It is something that can be produced by stationary electric charges. Another charge, when placed in an electric field, gives rise to an electric force. This can cause either static electricity, where the charges do not move, or it can drive the flow of electric charge if the material is a conductor. How is a magnetic field formed? It can be produced by the motion of electric charges, such as an electric current which is flowing across a wire. What this does is it gives rise to a magnetic force. This magnetic force is also